Welcome back for another episode of the GE Honesty podcast. Today, we're joined by someone who has spent decades at the intersection of science, genetics, and biosafety. Dr. Jack Heinemann is a professor at the University of Canterbury, where he directs the Centre for Integrated Research in Biosafety. Previously, he worked as a staff fellow at the National Institutes of Health in the United States. He served as a technical expert on gene technology under the United Nations roster of experts to the Swiss National Academy of Sciences, and has been a member of the ad hoc technical expert group of the Cartagena Protocol for Biosafety for the most of the last 20 years. Jack has published extensively on the issue of genetic engineering in the international peer-reviewed literature. He's become one of the most recognized scientific voices on genetic engineering. So Jack's been a vocal contributor to the discussion of how GE risks are being assessed and how those promises of benefits are being presented to the public. And at a time when the government is trying to fast-track the gene technology bill, his perspective feels more important than ever. So in this episode, we'll explore the flaws he sees in how GE is being misrepresented to the public and what this means for New Zealanders who may have no idea or realise how close this issue is to their dinner plate and their environment. Thank you for watching.
Excellent. All right, we're away, Jack. I've kind of vicariously lived through your work, through interviews and all sorts online, so it's actually really nice to be able to sit across from you and do the interviewing this time. So thanks for being here, mate. I appreciate it. I wanted to the reason I'm here, is because of a piece of legislation that the government is proposing called the Gene Technology Bill, which has a lot of implications for New Zealanders, for food, for farming, medical applications and all sorts. So I think it's really important that the public understand what that all means for them. And I think for the most part, there's probably people are information poor on a lot of that stuff. So I wanted to kind of start the conversation, I guess, on just kind of setting the groundwork of what gene technology is, what gene editing is. And perhaps you can just explain, what are the various applications of gene technology, just for a simpleton like me? What are the gene editing techniques that are coming out later? And just, a quick breakdown.
Sure. So gene technology is a way to intervene in a genome much more quickly than we would have been able to do by waiting for a change to happen and then finding that change, finding the organism with that change and amplifying it. It is a technology, and that simply means that humans can make what they want happen faster. And by faster, I mean both in time and at scale, in numbers. Right. So the original kind of biotechnology, when it came to, say, agriculture and breeding crops or livestock, the original technology was how you identify a trait in an organism that you want. And that took skill. I mean, that's thousands of years of human intellectual endeavor that went into the precursors of the organisms we currently use in agriculture. By being astutely aware of what it is that made that a useful variant of the species, and then having the skills to amplify it. We were able to further accelerate those kinds of technologies by having agents that can change genes. And the first kinds of agents that we adopted for this were chemical and radiation mutagens. Those also accelerate the rate of change in a genome. But once that happens, you still have to have people who recognize the qualities and the outcome they want. The vast majority of those organisms who have been exposed to a chemical and a radiation mutagen are not what you want. They usually perform even less well than what you began with. So you're looking for that rare variant that's useful. Around the late 1960s, early 1970s, there was a real advance in the ability now to intervene at the DNA level. So we understood now the relationship, or at least we understood better, the relationship between DNA, genes, and traits in organisms. And we started to develop the tools that allowed us to make those changes specifically at the DNA level. Those technologies are gene technologies. So they come out of the family of technology, biotechnology. We use that term to specifically mean the tools that work at a molecular scale, specifically on our genomes or the genomes of the organisms that we're targeting. And those tools have evolved over time. The kinds of tools that we have produce things that people are pretty familiar with usually. transgenic genetically modified organisms. But gene editing also produces genetically modified organisms. It is a way we use a technology to change the genome at our will. Gene editing is a variant or a branch of gene technology, and it's one that's just as old as the use of transgenes. It's just that it isn't as commonly known because it hasn't been a very effective tool or efficient tool, particularly in plants, until more recent decades, and in particular with the discovery of CRISPR-Cas. That kind of genome editor works very efficiently in all species and has now made it possible to use gene editing competitively with other kinds of gene technology, such as the use of a transgene. And the famous transgene kinds of organisms are herbicide-resistant crop plants or crop plants that make an insecticide. And that's the commercial-facing use of genetically modified organisms. But there's lots and lots of other ways we use gene technology that have nothing to do with producing a genetically modified organism to sell to you. That's basic research to understand how genes work. It might be to construct an organism for the production or overproduction of a desired metabolite or a protein or something like this. But the use of that gene technology isn't about making a GMO and having to release that GMO into the environment. A very small part of all gene technology is the part that we end up talking about the most, which is usually the commercialization of plants and livestock, crop plants and livestock, and it dominates our discussion. So there's a tremendous amount of use of gene technology that isn't about that, but there's almost no discussion about that, and it's all about releasing them into the environment, and the complaints by those minority of science and technology and commerce that's involved in that area, the complaints they have about not being able to release them fast enough. And this gene technology bill is meant to address that complaint, but it's not based on a true evidence-informed evaluation of whether that complaint is even valid.
Okay, just to step back there. When you say transgenic plants, what do you mean on that?
Right. So when people talk about transgenes, they mean taking a relatively large piece of DNA, size of a gene, from one species and inserting it into the genome of another species. And presently, there's a type of misleading campaign to make you believe that that's the only way you make a GMO. But since the 1970s, we've been able to do that, and we've been able to do gene editing with earlier tools than CRISPR-Cas in different species, including animals and fungi and bacteria. We've done it now for decades, and we've always known that both processes produce genetically modified organisms. And it isn't because it's just a word salad semantic game. We categorize them as products of gene technology, usually shorthand them as genetically modified organisms, because they have recognized risk potential to cause harm, and harm that can be controlled by a judicious, prudent, studious use of this technology and risk assessment and risk management that makes the use of this acceptable. It's a technology, which means that it gets ever better at producing what we want faster at larger scales. But all technologies also produce things we don't want faster and at bigger scales. We have the technology to make airplanes bigger and faster than ever before, but no one would ever contemplate not regulating them. Or only saying to Boeing, go ahead, we trust you. We don't have to check it after you've built it. But that's exactly what's being proposed here in this gene technology bill. It's if you tell us what you were trying to make, and if you tell us that we should trust you to make what you think you want to make, then we won't ever look. We won't ever check. This is a fundamental technology, and biology is a fundamental force of nature. Not only is it at least as important and powerful as aerospace. Not only that, but it has the ability to change itself after we release it. An airplane can't change itself, right? It's not a transformer. It can't suddenly then become an automobile or a bullet. It is what it is until it is destroyed. But a genome that's been modified by us, released into the environment, it works by its own rules from that point on. So this technology is both powerful in the way all regulated technologies are, and it has that attribute of its ability to change itself over time in ways we can't control and really can't predict.
Okay. And then there's another piece of this, which is the gene editing, right? Which is a later technique within the gene technology.
I'll just correct you. It's not a later technique. It emerged in science at the same time as transgenesis, right? There are some more recent tools. The difference is that instead of, we wouldn't say that because we can put a bit into an electric drill to drive a screw, that we never had the ability to drive screws before we had electric screwdrivers, right? So that's what's evolved. We have tools that are faster and more efficient, more scalable for using gene editing as a technique than we had previously, but we've had tools for gene editing since the 1970s.
Thank you for clarifying. So gene editing, as far as I understand, do correct me again, is you're not adding foreign DNA.
You might not intend to.
Okay, what do you mean by that?
All right. With gene editing, you can add foreign DNA. There's no question about it. And the Gene Tech Bill recognizes that. If you want to use gene editing as a way to insert a transgene, you can. There are ways to use gene editing where that's not your intention. Your intention is only to create damage in a genome and let that genome repair. And that's a use where they're proposing to deregulate it, right? Now, nobody does this, right? Nobody uses gene editing with the intention of not inserting DNA and not inserting DNA. DNA is in some mixture of cells that come out of your reaction inserted. And that DNA is often from other species for a variety of different reasons. But you can hunt among those products and usually find some that don't have added DNA, but you have to hunt for them. And this is the big flaw of the bill. It doesn't require people to ensure that the one that they did select and then intend to release into the environment is one that didn't have foreign DNA inserted into the genome, because you can't rely on that as being the outcome of using any gene editing technique.
Okay, because I guess the definitions are really important, the way they're characterized, because gene editing has been said, it's more precise, it's more efficient, we're not adding any DNA, so it's more closer to nature than. What is your take on that?
Right. So the whole idea is that somehow it only matters if it looks like nature it only matters to society if it does or doesn't look like nature. The U.S. National Academies has explained this really well, but it's been broadly misunderstood. What can happen, as I mentioned before, gene editing can be used in a way where you only intend to create damage in a DNA molecule, and then when the cell tries to repair that damage, which it usually has to do or die. So all our cells have the ability to repair DNA damage, whether or not it's caused by a gene editor. So if it's a photon from the sun, or UV radiation, we have the ability to repair. And that's what they want to make the metaphor about, that the damage is the same kind of damage if it's made by a gene editor or UV radiation from the sun. But that's misleading in a number of ways. However, even if you agree or accept that gene editing is no different from spontaneous events that happen without the use of a gene editor, even if you accept that, you have to hunt among those who have experienced the gene editor for the ones who do meet that expectation. And this is because, first off, when an organism is hit by UV radiation, they're not simultaneously also hit with DNA from other species. But when I use a gene editor, I am introducing both a gene editor and DNA from other species at the same time. I can't help to. It might be the way I get my gene editor into the cell. I may introduce it as a piece of DNA, which then has to produce a protein, which is a nuclease that causes the damage. That gene is from another species. And when the damage is caused, the damage might be repaired using the DNA from the other species, which is the nuclease gene itself or any of the other genes around it, which I had to use for my process. But also, many of the buffers we use in a laboratory have biological origins. And so what happens is, under the conditions that take up the gene editor, the cells also take up DNA from the buffers I'm using to hold those cells. And those buffers come from cows, cow juice. They come from yeast. They come from all sorts of different places. So at the same time I'm introducing a genome editor, I'm introducing DNA from a variety of species. And finally, and really specifically for, say, CRISPR-Cas, CRISPR-Cas is a two-component system. It's got a nuclease that causes the damage. But it's also got a little piece of RNA or DNA that we call a guide. And this is where you get those terms precision. It is the guide that directs the nuclease to cause damage where you want it to be caused. And these guides are synthesized in machines. And these machines are synthesizing on a commercial scale guides for all sorts of different people, all sorts of different species simultaneously. In a recent worldwide evaluation of the purity of the guides that have been provided on order, they found small contaminating contributions from 7 or 8 different species at once. So the commercial suppliers of those guides will also be providing you with nucleic acids from multiple species. So in 3 very important ways, when I introduce damage using a gene editor, I also do that at the same time as I provide that cell with DNA from other species. That's why even if I don't intend to have DNA or a new gene inserted into that genome, even if I don't intend to, I can't be sure I haven't. And I have to retrospectively determine amongst all the different products I make. There's hundreds to billions of cells that I expose to this when I do it. I have to search among them for those who are what I said they were. They have no changes that I didn't intend to make, including the insertion of DNA from other species. That you don't have to worry about with the sun. The sun is not contaminated with DNA from other species.
So we've obviously run a social media presence on this issue, particularly about the bill and just trying to get information out there. But one of the most common surprising misconceptions I've seen is a lot of people who seem to think that all fruit and veg is somewhat derived from genetic engineering, and that's been happening naturally over whatever X amount of generations. So, for example, a lot of people think seedless grapes are genetically engineered. They think the red kiwi fruit is genetically engineered. Is that something that you come across often?
Well, it's also part of the way people are manipulated. So as I said before, biotechnology is a continuum. The very earliest kinds of biotechnology were people who studiously selected the traits in organisms that they wanted to select. And in that way, they did accelerate the modification of species. If you look at, say, the evolution of the modern corn plant from its ancestors, it is, in choosing among words to describe it, metaphorical words, modified from its ancestors. But we didn't intervene specifically in its genome to do it. These technologies have their limitations and boundaries. The kinds of technology, biotechnology, that people use when they're breeding, watching for a spontaneous trait to emerge, and then amplifying it through breeding, has a different scalability than using gene technology. That's why gene technology is being so hyped and pushed, because it has a scalability that increases the potential for control and profit. Now, that's not necessarily a bad thing. We might get all sorts of plants and animals that people find desirable. Nothing stops us from doing that anyway, even without this bill. We can do that in New Zealand right now. And we've had 40 years to do it with gene technology, but haven't. And nobody else in the world really has either. But setting that observation aside, this is where we have over decades had our language thrown back at us. Early on in the 70s, the most popular way to describe the use of a gene technology was to produce a genetically engineered organism. The industry really pushed hard to change that to genetically modified organism, because then they could say, but we've been modifying organisms ever since agriculture began 10,000 years ago. And really, we've been doing it since before then. And then they use that kind of, it's all modification at some level, but they confuse two different things. One is a modification in evolutionary terms, where a species trait mix is changed over time, from a gene technology approach, where a specific gene or trait is changed in the individuals that you're working with. So that happened. And then they wanted to say, all right, we've given up on genetically modified organism. All of you already believe that a genetically modified organism is a gene technology where we put in a transgene. So we're going to say gene editing isn't making GMOs, because you guys have become fixated on transgenics. We're now going to use that against you to say, well, that's what you think a GMO is. We've solved the problem. We have a different gene technology that doesn't make them. And this is all, in my view, as a geneticist and as a genetic engineer. I mean, that is my science. I do genetic engineering. I use gene technology. That, to me, is just sleight of hand. The point is, these are different types of techniques within the family of gene technologies that make specific integrated changes in a genome and are scalable in the way that driving screws is scalable and have become more and more industrially scalable as we went from screwdrivers to electric handheld drills to drive those.
When plants express naturally through pollination, as nature intended, do you know, or can you comment on, do those genes express in negative ways in nature to things that we wouldn't want, or is it more common when gene technologies are involved in the first place?
I see.
Do you know what I mean?
I don't know that I know exactly what you mean. But certainly agriculture is a story of enriching in plants and animals that we want to use in agriculture, enriching in them the traits we want. Right. And getting rid of the traits we don't want. Plants make toxins to us. Plants make anti-nutrients, right? We try to select for plants that make fewer toxins, fewer anti-nutrients, and more nutrients, or have what other value we want from them. And up until 50, 60 years ago, that was mainly done through breeding. Now, in some ways, it could be possible to accelerate that using gene technology. There's two different ways. One way is to use the gene technology to specifically target the toxin or anti-nutrient pathway, or to use the gene technology to enrich for those who have spontaneous mutations that have achieved that, but aren't specifically the use of a gene technology to change that genome. The gene technology helps us identify and enrich the ones we want. So that's what I'm saying. Most gene technology doesn't have to be used to make a GMO. So you can use it in those various ways. The use of a gene technology automatically makes something more harmful to us than if it were to arise spontaneously in nature. And this, I'm getting back to what the U.S. National Academy said. And the U.S. National Academy said no. If you have exactly the same mutation arise through the use of gene technology or UV radiation from sunlight, one won't be more harmful to us than the other. That's been misused by a large proportion of the scientific community, and definitely also the biotechnology and commercial community, to say, therefore, we shouldn't regulate one and not the other. Okay. But this is the fallacy. The Academy said that they may be equally harmful, but the harm may be unacceptable from both. That is not a reason to deregulate the use of a gene technology for making something purposefully or accidentally harmful. So it's a fallacy. It's a laziness of regulation to simply say, well, because two things of different origin can be equally harmful, and one of those origins I can control and one I can't, therefore I won't control either. And here's an example, right? About 2 billion years ago, in some caves in Africa, there was a spontaneous nuclear reaction that lasted, hundreds of millions of years. It could happen back then because the particular isotopes that were available on Earth were at a higher proportion back then than they are now because of decay. And they were concentrated there, and the conditions were just right to have a critical self-sustaining nuclear reaction for hundreds of millions of years. That happened without any human intervention. Humans didn't even exist then. That doesn't mean, because that could happen naturally, without human intervention on Earth, that we should open up a nuclear power plant to the atmosphere or deregulate nuclear power plants, not make them safe. This is a very strange argument to me, and there's a difference between it happening in nature and it happening by a technology, and that's the scalability. So what happens because of our use of a technology is the rate and number of potentially harmful outcomes is unnatural when it comes from the use of a gene technology versus nature. And that's not because nature is benign. We know things like bad viruses that cause pandemics, which might arise spontaneously in nature, and probably do arise spontaneously in nature all the time, but very rarely cause pandemics. And that is because when they do emerge, they emerge in really infinitesimally small numbers. When it happens randomly in nature, in random places at random times, versus in a laboratory where I can make 100 million in a day. That's what makes it a technology. That's where regulation is effective, because regulation affects the harm that can come from the unnatural scales at which a harmful thing can be made.
So we've been told by politicians that there's a ban on genetic engineering in New Zealand and it's holding us back somewhat. What do you make of that statement?
Okay, there's two statements. One that there's a ban and one that it's holding us back. First off, there is no ban. And when that was pointed out to certain politicians, then they introduced the word effective ban in front of it. So again, it's part of what I think looks like manipulation. New Zealand has always been able to make genetically modified organisms using the full suite of techniques we have available to us in gene technology. There was a very brief period around the turn of the century where, because of violations to the Has-No Act, there was a moratorium for about a year or two. But that was it. Other than that, continuously, for all of time, we have had either no legislation to prevent us from doing it, or legislation that allowed us to do it, but only under certain circumstances where we've done a risk assessment first. And that's the Hazardous Substances and New Organisms Act that since 1996. So we can make any kind of GMO anybody else in the world can make. We just have to go through what most of the world goes through, a regulated process. Likewise, we could make jet airplanes. We would just have to do so through a regulated process. We choose to make these things using those technologies and complying with a reasonable regulated process, or we choose not to do them. The other question is, we've been held back. In my opinion, there's no evidence at all that New Zealand has suffered any damage from its judicious use of genetic engineering to make GMOs for release into the environment. Because remember, that's a small part of what anybody in any country does, is make GMOs for release into the environment. The countries that have done that have mainly done so using crop plants. And those are countries that are big and flat in the Americas or are deserts like Australia. They've done it because they can grow massive monocultures. And the type of trait that they put into those crops industrializes the production process. It reduces their labor costs. If you make a plant resistant to a herbicide, then you just need an airplane to fly over 100 million hectares and apply the herbicide. That's one person, one plane, instead of having armies of people doing your weeding. And they can do that because they can grow massive monocultures. If you have an agro-ecosystem like most European countries, where it's lots of different crops in a patchwork of small farms, that model doesn't work. Yet, when you compare the yields of their crops to the yields of the crops in the Americas, they're the same or higher. It's a different agricultural model. The model works for countries for which the gene technology is coupled with another technology, usually a chemical-based technology for pest control. It doesn't work where it's not scalable. So in a more patchwork, most of our food, there's some debate about what this number is, but the numbers I've seen vary from 40% to 80% of actual food comes from smallholder farmers. 40 to 80% of what we eat does not come from the agroecosystems that use genetically modified organisms and pest control using airplanes. But a lot of our crops do come from there if they're maize, soybeans, canola, cotton. And the reason is then because those countries can industrialize those monocultures, but we don't eat those. We use them in textiles or materials, or we use them for animal feed, so indirectly to our food, but very indirectly, and not really the best use of our calorie production. Or we put them into the petrol tanks of cars. Something like 60% of the U.S. corn harvest becomes biofuel.
I didn't know that.
By law.
Oh, okay.
It's got the priority use. So U.S. corn is not feeding people. It's feeding their automobiles. And that also allows the U.S. to not put pressure on car manufacturers to improve automobile engine efficiencies. So it's a complex network of reasons. So I guess the point is there's no evidence at all that New Zealand agriculture would look substantially different had we decided to go the same pathway as the U.S. We don't have, all of New Zealand would fit in a corner of the U.S. Midwest. We don't have those great big open plains like Brazil and Argentina and the U.S. that make them amenable to that kind of industrialization and economy of scale using those types of traits. Since the 1970s, genetic engineers have promised to make crops that are more drought tolerant, salt tolerant, heat tolerant. They would fix their own nitrogen. 50, 60-year-old promises never delivered upon. Breeding, though, has significantly, non-gene technology, but good old-fashioned biotechnology plant breeding has produced massive gains in drought tolerance, heat, and salt tolerance.
Are you referring to marker-assisted breeding?
I'm referring to that, and all other kinds of breeding have made these advancements without the need for gene technology, and the specific attempt to do it by gene technology has never delivered us a product in all this time. So what is New Zealand missing out on? If you look at New Zealand's productivity in both the horticulture and livestock, we do as well as anybody, and in many cases better than everybody. We're not missing out on anything. It could be in the future that there will be some kinds of traits or adaptations that we just can't achieve in a time scale that's necessary without the use of a gene technology. That's a hypothetical because we don't know for sure that gene technology will ever deliver those traits. But it might be that that's our last hope. We can do it then because we have the legislation that permits it. All we need to do is have people who have both a good idea and have the ability to deliver that idea using a gene technology. And that's where I think the problem is. gene technology is not a straightforward way to deliver the kinds of things people say we need. Whereas agroecology, plant breeding, these have worked. They're true, but we underfund them while we throw our money, our resources, our attention, our anxiety into technologies that have not delivered.
Okay, so in the US, there's what, 4 main crops, GMO crops that you mentioned earlier. And who owns those? Who owns those? Is it one company, 2 companies?
There is a massive concentration in the seed industry. So the big crops there are maize and soybean, cotton, not so much canola, but there's a few others like sugar beet are almost 100% genetically modified. And I'm probably forgetting somebody. But what genetic engineering has done, what gene technology has done, is made a genome ownable. Until gene technology, you could have intellectual property protection on a plant or an animal, but it was a much less strict kind of ownership. The plant or animal had to have and display all of the unique traits that you were owning by registering that plant or animal. And if it didn't breed true, then you no longer owned it. That meant that you didn't own the germplasm. Only in special cases where it was clonally propagated could you kind of own the germplasm. The other special case, called a biological patent, was hybrid vigor. So if you kept secret the 2 parents who, when they mated, produced a superior offspring, you could control that offspring because further breeding of the offspring, the trait disappeared. And that's hybrid vigor. So that was maize. That was the big innovation for maize from the 1920s through to the 1960s. But you couldn't do that for soybean, couldn't do that for sugar beets. Open pollinated things you couldn't do that for until you could put a utility patent onto a genome that had been manipulated using gene technology. This is one of the reasons why it's scalable. You can own a germplasm. You can own a genome in a way you never could before. And that's another reason why when we accelerate the production of things using gene technology, good things get accelerated no more quickly than bad things, whether you intend them to or not. And it's a way that doesn't happen through other biotechnology, such as conventional breeding, because those types of intellectual property instruments that can be applied to the genomes manipulated using gene technology are so powerful that they create new kinds of context for those plants to be in. And that's what you're observing. You're observing a collapse in the biodiversity of those major crop plants because to couple them with the herbicide resistance then gives somebody ownership of that entire germplasm. And they only breed those for the purposes of selling them to their biggest farmers. The rest of the world, like the seeds that might be offered to African countries, are the ones that are largely just adapted for use in the Americas because that's the big market, and they're not breeding for the rest of the world. That kind of concentration in the industry is really profound. In the U.S., in only a few decades, the U.S. went from being the country with the largest seed saving and exchange in soybeans to none, where seed saving and exchange is illegal because of patent law, contract law.
Illegal? Made illegal?
Mm.
Wow.
Because it's a violation of either patent or contract law. This was the case with Percy Schmeiser in Canada, right? You may know this case. His farm was found to have canola plants that were resistant to the herbicide Roundup. And the owner of the patent for the trait that made canola able to grow even in Roundup became aware that those plants were in his field, even though he never intended them to be. He probably got contaminated by trucks that were harvesting these seeds from other farms and driving down the road. But the moment he became aware of it, because he tested some Roundup on some of his crops and found that they survived, he became subject to the laws that govern intellectual property rights And the Canadian Supreme Court determined that regardless of whether or not you get a benefit from that technology, and regardless of your intention to use that technology, once you know you have it, you owe a rent to the intellectual property rights owner. And that is what they got him on. He knew he had it at some point, even if it was a minority, and therefore he owed money to the patent holder, Monsanto. And that's because of the instrument. It's a utility or process-based patent. It's a fundamental patent with far more power than the kinds of intellectual property rights instruments that had up until then been dominant in agriculture.
Correct me if I'm wrong again, they're not able to save those seeds and go again, right?
That very reason.
I want to go back to the bill again, the Gene Tech bill. What do you make of the current state of the bill? And is there anything in there that really concerns you or is a blind spot?
Absolutely. My number one issue with the Gene Tech bill is the proposal to take some types of techniques, such as gene editing as they define it, and some kinds of products of gene editing, certain kinds of organisms, and exempt them from any legislative oversight. If you looked at the original press releases from the Ministry of Business, Innovation, and Employment, they had some tables, and those tables had things in green boxes and in blue boxes. The real big change in the bill was to say the things in green boxes, they're no longer even going to be covered by legislation. We're just going to define them as not being GMOs arbitrarily, based on arbitrary criteria that we invented. And the things in blue boxes, we'll still call those GMOs, but we will regulate them, some of them, in a less onerous fashion. Now, if you just look at the blue boxes is what we would call a tiered regulatory scheme. And the idea is to say that some things maybe could be regulated more lightly. So we put them in a lower risk tier. Because they're in a lower risk tier, we can regulate them more lightly. And some things we regulate more stringently. They're in an upper risk tier. There's some argument to be made for that. And for those who have been hungry for or feel that somehow their ability to save the world has been hampered by the current regulatory scheme, that might be some relief. But what's concerning is that green box, where you say, just because I've decided, based on my metaphorical understanding of how biology works and evolution works, that everything in these green boxes will always only make things that society doesn't care about, that won't create any kind of legitimately regulated harm, because I've decided that in advance, I'm going to take away all the tools society has to protect itself by deregulating, descoping. And that's my biggest concern. I don't think there should be green boxes. I think all gene technology techniques should only be used in registered containment facilities. I'm not against having a tiered outcome, blue boxes. So if you have ensured that only the organisms you intended to expose to those tools have been exposed, and then you have characterized any of the products to confirm that they are what you intended them to be, okay, then maybe you can have, in some cases, a much less stringent or impactful kind of regulation on those products. But you still have to make them under conditions where you don't create unintended harmful outcomes, because you can't control exposures, you can't control the knowledge of the personnel, the training of the personnel who are using it. And we already know that you can get gene editing kits over the internet. And if you deregulate their use, you then take away any possibility of controlling the various species and people who are exposed when someone chooses to use them.
If this bit, let's play a scenario out here. If this bill does pass and it gets through, how do you kind of foresee this changing farming, our food systems? What would you be expecting in that scenario? We've already seen how it plays out overseas, but I'm just curious to get your take.
Well, we haven't seen how it plays out overseas. Right now, there's almost no contribution whatsoever anywhere on Earth to agriculture from gene editing. Just like in the early heady days of the 70s, 80s, and 90s, there's lots of promises about what gene editing will do. Right now, there's no commercial impact. There's been maybe half a dozen, at most 10 or 12, products that have gotten to the point of commercialization, and a lot of them have already disappeared. So we don't have any big blockbusters out there. That doesn't mean we won't. Maybe there still will be, but we can't say from our experience so far that it has changed agriculture in any way, any material change. The other thing is, because we've always had this power, we just haven't had it in plants as efficiently as we have it now, but we've had it in animals, bacteria, and fungi in very powerful ways for many decades. And it hasn't made a significant contribution to agriculture. Well, based on that, you might extrapolate a much more modest appraisal of what gene editing can do. I forecast that we're going to get a lot of boutique novelty, but we're not going to get fundamental changes to our agroecosystems. We might get more apples that are different colored. We might get more grape varieties that don't have seeds, but these are not going to save the world. And most likely, the changes that we get will be ones that cycle through. So for 5 years, we'll have red apples, and then for 5 years, we'll have yellow apples, and then for 5 years after that, we'll have green and yellow apples or something else, because they have some novelty factor, but aren't a major component major component of agriculture and the kinds of traits that we are being sold. Drought tolerance, heat tolerance, things like this. Better pest control, right? So we'll get lots of little novelty, but we won't get any blockbusters. That's my initial prediction, with possibly the exception of one or two, but they're likely going to be, if we do make an exception, an exceptional contribution to agriculture, it's going to be in something that we already produce too much of in the bad way. Just as happened when we used genetic engineering to make herbicide-tolerant crops, we will simply grow them again in unsustainable conditions like monocultures, with unsustainable ecosystem changes to support those monocultures. So even if gene technology does give us some of these really useful traits, we will probably misuse them by concentrating them again in unsustainable agri-ecosystems.
So would you, just to clarify, would you define gene editing as still genetic modification?
Absolutely. It's just a type of gene technology.
Okay, because it's being told that it isn't.
I know, and it's a manipulation. It has always been defined as a gene technology. And as I say, there were review papers published in 1980 that referred to gene editing from the 70s. And in animals, fungi, and bacteria, we've had gene editing since the 1980s and 90s. It's only really plants. And it's the plant biotechnologists whose voices you're largely hearing jumping up and down about this, because CRISPR-Cas as a technique is a breakthrough in that it increases that power in plants, because it increases the power in all species at once. So now that electric screwdriver can be used on that species too.
So no silver bullets yet as far as these promises. In 30 years of GMOs, we've largely got a few commodity crops and a few winners.
You have pest control traits in commodity crops, and you have conventional breeding providing us all the vast majority of everything else.
Well, it's also, I guess, if you look at what the market wants, what the consumers want, consumers are getting more smarter these days about food and where it comes from. And that's where the trends are going. And that's something that New Zealand is uniquely positioned to offer, as that with that competitive advantage of being GE/GMO free. It seems like a massive backward step to walk away from that.
Well, it's possible, and I think you have to talk to the industry about that.
Yeah.
But I guess the only counter argument I can think of to what you're saying is that novelty itself does drive revenue. And if we make boutique things, I mean, kiwi fruit and other, boutique entries into the world's caloric intake, that may still be in the short term economically useful and viable. If that is how gene editing, which requires a change to gene technology X, if that is what I was being told, I would be more receptive to it. We're going to make a little tinkering. We're instead of dyeing your hair with chemicals, we're going to be able to dye your hair with gene editing just so that you can see blondes, brunettes, and redheads as you like. Okay. At least be honest about it. It is a boutique thing, and that's our market model. That's our industrial model. But it's not being. It's being sold to us as the only way to be competitive, the only way for the world to feed itself, et cetera, et cetera. And it's wishful thinking. I mean, you have to do more than continue to make promises on a gene technology. You have to start delivering. And the idea that regulation is the cause of you not delivering itself needs evidence. I find very little evidence other than particularly plant biotechnologists writing papers where they say regulation is what's holding them back. I don't really see independent literature evidence from credible types of researchers that demonstrate the reason we don't have a particular kind of plant, animal, or trait is because of regulation.
I'm just mindful of your time before we wrap up, but is there any message that you would give to New Zealanders who, new to the subject, don't really know what this bill's about, don't know what G or GMOs are, maybe only just waking up to it? Is there any advice that you would give to those people?
Always be concerned when a powerful technology asks to be deregulated. The one thing a democracy has to keep it a democracy is regulation. It is your democratic voice to say how a technology is used safely and for the benefit of your society. If you do not have laws to control a technology, you don't have a voice. Regulation is not the evil force here. Regulation is used to control forces that result in bad things. That doesn't mean all regulation is good, perfect, or finely tuned, or proportional, as they would like to say. But before you give up that power, be sure you do so with your eyes wide open.
Okay. And is there any reason why you're able to speak up, but others don't, perhaps? Or the other side of the fence?
No, there's no reason. People choose to speak or they don't choose to speak. One thing that I can say at this end of my career is the idealistic view of a university and university academics as being selfless individuals who will speak truth to power, even though it may come at the detriment of their own careers. That is unfortunately a very romantic view of what the universities are. There are still people who do this, but there are ever more forces and controls that try to prevent or discourage that kind of attribute. The way we select people for universities has nothing to do with their fortitude or willingness to speak truth to power and do so as honestly as they can. It has to do with how many papers they can publish. And how many papers they can publish has a lot to do with how much grant money they can get. And how much grant money they can get has a lot to do with what industries they don't piss off.
I'll probably wrap it up there, Jack, unless there's anything else you want to mention, really, that we haven't... No? All good?
The one thing, I'm not sure if you want to use this, and you would probably have to splice it in somewhere, but when you ask the question about using these techniques to make things that don't have foreign DNA, a great example is the hornless cattle example. I don't know if you're familiar with it, but in that case, they used a technique, a gene editing technique, with a nuclease called a TALEN instead of a CRISPR-Cas system. And that should be even less vulnerable to the insertion of foreign DNA than CRISPR-Cas. And the company said, when they made the hornless cattle using this technique, that they did all of the background checks and there was no foreign DNA. Later, when the Food and Drug Administration got a hold of their data, they found 4,000 new nucleotides in that cattle genome, and it was DNA from bacteria. Right? That company not only believed it couldn't add external DNA. It then said that it checked and didn't find any. And the reason? Because it never checked for the most likely DNA that could become inserted, which was the DNA in their own reactions. So my point is, it is possible for some uses of these techniques to produce organisms with no unintended insertions of DNA, but you can't rely on any example being that. You have to check, and you have to check that they checked right.
Yeah. I have one more question for you. I've just remembered. This comes up a lot with people that I speak to on this issue, in that once you release a genetically modified organism, a plant, what have you, it will eventually contaminate everything. And the way I understand that is it would permeate across other species, right? So could you...
Yeah, there's the potential. There's, of course, the potential. Any organism, any gene has the potential to amplify in the environment. I mean, that is how we go from a rare mutant, like I was saying before. There's all sorts of viruses being made all the time around the world, but only one of that type in one place at one time. That's a very small number. And the chances of it becoming a population are small. That's why breeding has a kind of scalable safety factor built in. So in theory, yes, we could make a GMO that will spread for reasons that we can't even understand or predict. That doesn't mean it will, but it can. The difference here, though, which is concerning with the Gene Tech Bill, is that up until now, when somebody has made on purpose a genetically modified organism to release into the environment, they've also provided the tools for detecting it. That means that if you're an industry who is trying to keep genetically modified organisms out of your product line, you have the tools to at least screen that product line, or those who sell it to you have the tools to ensure that their products are, at least to some level, free of these things. But the Gene Technology Bill, by taking organisms outside of the legislative scope, no longer requires anyone to tell you what they did. And if they're inserting on purpose or accidentally DNA from different species into all sorts of different kinds of organisms that can contaminate all sorts of different product lines, which could be detected by random screens that you can't predict in the future, then yes, that's a problem. As an example, you can get kits to gene edit yeast, and you know yeast is used in all sorts of things. It's not used in just the obvious bread making and wine and beer. It's also used as a foundation organism for producing all sorts of other things in processed food lines. So if everybody is making willy-nilly and even unintentionally gene-edited yeast when they're playing with their gene editing kits doing something else, but those yeast are able to survive in the environment, then we get all sorts of background contamination that can disrupt supply chains. Because if a country, and this is important, countries do have some tolerance to contaminated food from genetically modified organisms, but only on the condition that they know what the organism was. It has to have been approved by a regulator somewhere and found to be safe. Then they will tolerate contamination, even if they don't want it, up to a threshold level. But an unknown GMO contaminating your food, zero tolerance. This is what got us in the years after Corngate, when Japan returned corn shipments because there was an unknown genetically modified organism in there. And it turned out our silos had been contaminated by a different crop plant. So if you don't know what that GMO is, zero tolerance in many countries, EU, Brazil. They will tolerate if you do know. And this gene bill, this new gene bill, will take away the power to know that and verify that it's a safe organism. That will put the burden on the producer of the product in New Zealand, who is a relatively small market, right? And can't afford to do 8,000 tests to try to figure out what it is.
Okay. Amazing, Jack. Thank you so much, mate. I appreciate it. Awesome.